Okay, good. Thank you. Okay, so let me recap a little bit what we did 2 days ago. We learned how to, that generic quantum states can be written as tensors, okay? And then this tensor can be decomposed in a way that it can be useful for you in two different ways. One is to reduce the memory, okay? So reduce the amount of information you want to store. And two, in a ways that to figure out how to contract all of these tensors such that it's efficient, right? And we learned that 1D scenarios, or where you, or at least when you use matrix product states, then contractions can be always very efficient, okay? Also, we learned that this type of way of storing the information works really well and for area law states, okay? And then we were discussing about which states are area law. And we mentioned that if you take a local Hamiltonian, which is gapped, the ground state is area law, right? Then after the sessions, there were some questions, and I think maybe I should have also mentioned, for example, let's say you are in the critical, between two transitions, you're in the critical point, right? Is it area law? No, it's not area law. For example, in 1D, it follows a log law, okay? Log law are already much harder than area law, of course, because entanglement grows as the logarithm of the system size. It's not a constant. But since the log doesn't grow so much, if you have large enough bond dimension, you can manage to describe it quite well in some cases, okay? So that's one point. And of course, yeah, volume law, these are this kind of hopeless cases. Then another questions that I was, another comment that I wanted to mention to complete the discussion from Monday is that we show that for matrix product states, you can only basically describe exponential decay correlations, right? And we did the calculation. In 2D, actually, you can describe algebraic correlations. Okay, for like PEPs, for example, you can describe. But then, okay, there are other issues, as I mentioned before, for those states. Then there was another question that a few of you asked me. And the question is about thermostates. Okay, and I understand that, okay, so the confusion is is this. What I stated is that if you have a gapped Hamiltonian, you look at thermostate, okay? Now, by thermostate, I mean e to the minus beta h, the density matrix, okay? So this density matrix can be represented efficiently. Now, some of you say, but what if I take a wave function, right? And I do a quench at a fixed energy, right? Maybe it goes to e to the minus beta h. So the wave function doesn't go to e to the minus beta h. It's a different object, right? It's not a density matrix. It's a wave function. What happens is that if you look at a small portion of it, right? It, after it thermalizes, okay, it may be indistinguishable for all the local observables in that portion from the density matrix from a thermostate, okay? But they are different objects. And if I just look at the wave function that I did a quench and it's thermalizing, that is volume law, typically, okay? And so it cannot be described efficiently with tensor networks. Okay, so I hope I addressed some of the questions that I had from the last session. Are there other pressing questions? No. Okay, then I continue. What I would like to talk to you today, hopefully I can reach in this hour and a half, is to talk about how you can approximate states with, let's say, with matrix product states, and how to do add them up and then multiply with MPOs, with operators, okay, and how things scale differently once you do these operations. And then once you have these pieces, how to add them up and how to do multiplications, how to do ground state search. Okay, so hopefully we can get to ground state search by today. And tomorrow If all goes well, then we will do time evolution as well. Okay, sounds good. So this is what I'm trying to do. Okay. So one thing that is quite important, we show that from a Schmidt composition, you can always write a state as sum of A of some S, A, okay? And then you have some A on a portion A of the system. This can be any dimension, right? In any dimension, I take a system and partition into, I have A and B, okay? Okay, so I can always do this. And let's say the rank of this matrix is R. So this goes from 1 to R. Okay. Then I take another psi tilde, which is sum from A. So I take the same elements, okay, same states. But now, instead of going all the way to R, I go to a R prime, which is less than R. Okay? And now I want to see how different these two objects are. And so then I can compute the difference between them, which we can write it as the overlaps. Okay. Now, let's think about how to do this and what this really means. If I look at this thing here, this is the sum over A of SAA. Let me write it bigger. SAA square from 1 to big R, correct? Okay, because I'm summing all of them. I have all the terms. Here, this would be the sum over A, again of SAA square, from 1 only to R prime, correct? Because all the others are not there, so give you 0. And this is equal here and here, correct? Because it sums up only to R prime. So these two I can cancel, and then what I get here is this the sum for A that goes from R prime plus 1 to R of SAA square. Okay? So when you look at the singular values, and in many cases, okay, so let's look at singular values. Maybe I look at the log. The best case scenario is when this goes down exponentially. Okay? Yes, please.
But when you have like psi prime and psi, you have another sum which goes from 1 to R. Not
Yeah,
both sums.
but there are no states there, so the overlap is 0 here.
Oh.
Correct? Okay. So the best case scenarios is when this goes down exponentially. Then you're quite comfortable. You can choose a certain epsilon, okay? And below this, boom, you can truncate, and you have a really good approximation of your state, okay? And you can actually evaluate how big this thing is, or do an estimation of that. And of course, then in some cases, this may not decay exponentially. Then you need to be careful. And the point is that by looking at this quantity, you have a very good handle of how close you are to the state you want to represent. Okay, so in a sense, it's quite well controlled. Okay, so this is okay. Now, I wanted to describe to you how we can write the tensor networks in a way that later on doing a lot of calculations would be easier. Because let's say, okay, let me try to drive you, since today we want to talk about ground state. What will mean that I want to compute the ground state, okay? Okay, so I'll put it here so we have the goal in mind, and hopefully I will not erase it throughout the rest. Okay, so we will have a state, okay, which now we know we can represent like this, correct? And we have something that represents the Hamiltonian of the system. Again, this would be a matrix product operator. We know we can represent like this. Okay, so this is psi. And this is, let's say, the Hamiltonian H. And then to compute the expectation value, I need the bra, okay? So I will do this. Okay, so this structure here, now that you are a bit more familiar with the graphic representation, but I will go through the indices later on, I've already told you, just to give you an intuition of where we're going. Okay? This represents the expectation value of the energy. And so this, if I want to, using Schrödinger equation, I will write is equal to E times psi. Okay? So this is Schrödinger. And what we want to do is to find, try to find the lowest value of the energy, right? So we'll have to minimize this object here. So what would I vary is I will have to vary these wave functions here, right? Such that you get the lowest energy. Okay. Now, what you will have to do, you have to do a lot of these contractions and sums, okay? Both here and here. And the first thing that I would like to talk to you about is tools.
So you're taking the unnormalized state on the right.
This is psi. I will show you later on that it will simplify. We can make it normalized. Okay. So yes.
So is psi the eigenvector of H?
Huh?
Is psi the eigenvector of H?
Yes, what we want to find is psi that is the eigenvector of H that corresponds to lowest eigenvalue. This is what we want to find. But we can already start to write this, right? Okay, and if psi is the eigenvalue, this will be corresponding eigenvector. Okay, so this is what we want to find. Correct. Okay, so this is kind of the objective. And what I try to build now is tools that will help us to do these calculations efficiently. And the first tool that is very useful is to turn the state into a canonical form. And we will have two canonical forms, left canonical and right canonical. I will get to this in a moment. Let me start with the left canonical. And what do we mean by this? Okay. So the beginning, 2 days ago, I wrote something of this type. C, sigma 1, sigma 2, sigma L, sigma 1, sigma 2, sigma L. Okay? The state. And what I told you is that this portion here can be written as a tensor and so on and so forth. So let's do this now in more detail. So let's build the MPS that corresponds to this thing. How can we do this? Okay, we start with this object here. C, sigma 1, sigma 2, sigma L. And what we do, we reshape it. Okay, we reshape it as some phi, sigma 1 on one side, and sigma 2, sigma L on the other side. So now we think of it as I had a vector, and now I write it as a matrix. This was a vector 1 times 2 to the L, correct? And now I have a vector that is 2, a matrix that is 2 times 2 to the L minus 1. Fair enough? Okay. Now, once I have this, I can do a single value decomposition. SVD. And so once you do the single value decomposition, you get U with index sigma 1 and some auxiliary index A, 1. Then you have the single values, diagonal matrix, A1, A1. And then you have the V matrix, which with values A1 and then sigma 2, sigma L. You agree? So this is 2 times something, at most 2. Okay? That this is a diagonal matrix, at most 2 by 2 in this case. And then you have something that at most 2 times 2 to the L minus 1. Okay? Okay. And what we're going to do is to relabel this as some A, sigma 1, A1. Okay? So we just write it as a tensor in this form. So basically, it is a tensor of this type. Okay? Here you have sigma 1, and here you have A1.
So you are translating C to this phi.
Yeah, I reshape it to this phi. Okay? And then from this phi, I do a SVD. Okay? Good.
Why is this reshaping important?
Sorry?
Why is this reshaping important from?
Because I want to do an SVD so that I will have the physical indices here, and then I want to see all the other terms. So I want to single out. Whenever, you see, the goal is to write a state like this one, with many pieces that have a form like this. You have a sigma L here, okay? Then you have an AL here, and AL minus 1 here, okay? Okay. And okay, so this part I call it this way, and this part now I call it some other phi, which has indices, so I group them, okay? I will have A1 okay, and then sigma 2 all the way to sigma L. Okay? Fair enough? So the next step is to reshape this again. So I have A, sigma 1, A1. And now I will reshape this phi as I will bring the physical index here inside sigma 2. And then I will have sigma 3, sigma 4, all the way to sigma L. And what I do, again, single value decomposition over this object here. So I have A, sigma 1, A1. And then I have U, A1, sigma 2, A2. And then S, A2, A2, V dagger, A2, and then sigma 3, all the others until sigma L. Okay, I hope it's readable. Okay? So you still do the same steps. And now what you do, you recognize this as some A, sigma 2, with index A1, A2. So it has really the shape that we want. Okay? A physical index on top, auxiliary indices on the sides. And all of these things, I merge it together into something A2, sigma 3, sigma L.
A3, right?
Sorry?
AS, A2, A3 then. I mean, some different.
No. A1, A2. Then A2 goes here. There is no A3 yet.
So
It will come with a third singular value decomposition. Okay?
I'm talking about this S, A2 and something else.
A2, S is diagonal. It's always diagonal, right? Okay, now you can see what we are doing graphically is that we started from an object like this, for example, and slowly we are building the first A matrix, okay, and then we're building the second A matrix, and so on and so forth. You can see you can continue this process until you build all of it to be C sigma 1 sigma L equals to A sigma 1 A1 A1 A2 sigma 2 until A sigma L minus 1 sigma L. Okay? And your state is fully A matrices. Okay? So we can write it fine? Okay. So why is this useful? It's useful because, say we want to compute something of this type. Okay. Yes.
Small question that in that expression, the last one is sigma L and then the...
Oh, A, L minus 1. Not sigma. Thank you. Okay. So let's say I want to compute an object like this. What this means physically, this portion here, means sum of a sigma 1 to, let's say, sigma L of A sigma 1, A1, A sigma 2, A1, A2, until A sigma L, AL minus 1, AL, times sigma 1, sigma 2, until sigma L. Okay, so this, you see this portion here is indeed this state, correct? Now, if I want to do this product, okay, what does it mean? It means you're doing a sum. Okay, you have of, let me write it here, our state. Okay. So sum of all the various sigmas. And then you have the other state. So here you have the psi. Let's call it A L. Okay. And here you have A L. Okay. All of those states. Maybe A is not a very good label. Let's call it alpha. Okay. So you have A dagger, sigma 1 maybe prime, A1 prime, sigma 2 prime dagger, A1, let me do it bigger, sigma 2 prime dagger, A1 prime, A2 prime, all the way to A sigma L prime, AL minus 1 prime, AL prime. And then you close this, okay, with sigma 1 prime, sigma 2 prime, sigma L prime, sigma 1, sigma 2, sigma L. Okay?
So that is the leg open on one side.
Yes, we leave it open. Yeah. Okay. So this gives you delta function between all the sigmas. Sigma 1 is to be the same as sigma 1 prime. Sigma 2 equal to sigma 2 prime, etc. So So this is the sum over all the sigma 1, sigma 2, sigma L, or this thing here. So I start from the middle. A sigma 1 dagger, A1, A sigma 1, A1. Then you have A sigma 2, A1, A2, until A sigma L, AL minus 1, AL. And then A sigma 2 dagger, A1, A2 prime. Okay, this indices here, this index here will be A1, A2, but here the indices will be A1 prime, A2 prime. They don't need to be the same, right? But here we have a contraction, so sigma 1 and sigma 1 prime, then they have to be the same, right? But the A, they don't need to be the same. Okay. Now, the thing that you realize here is that since this is a unitary matrix, such that you have that this is delta A1, A1 prime. Okay? Because it's a unitary matrix there. Yes?
So this one is different one because you have open and
Yeah, I just took a piece.
okay.
I cut in two. For example, my state, I cut it in two, I take a piece of it.
But why does this inner product comes from this first?
Because I'm taking states here until a piece, right? Imagine you do, imagine, for example, you do a single value decomposition, you just take the A portion, right? The left portion. So then you take those states there. Okay? So this is identity. Okay? And then this also, these are unitary matrices. This also gives you identity here. Delta A2, A2 prime. And so on and so forth. So actually, a way to graphically see what is happening is that when you have something like this can be contracted quickly. It becomes becomes identity. Then you can further contract this quickly, becomes also identity. And in the end, you're left with identity again. Okay? So the contraction, and this is actually expected if you were doing, you expect also from Schmidt decomposition, right? So that's why they're called left canonical, is because when you start to do contraction from the left of MPSs in a left canonical form, you get identity matrix. So it's becomes very easily. And so now you can see already that when you want to do, when you want to do these contractions here, then all of this becomes identity, very easy to do. Okay, and you don't need to do them. Okay. Okay, so this is the first thing. Now, the same does not happen if you want to do things from, okay, let me do it here so I can save some space. Now, if you start from the right instead, okay, or if you have these states to add up, okay, then things are a little bit trickier because you cannot use the A matrices anymore because they don't have this property that when you contract from the right, you get identity matrix there. What you need to do is to use a right canonical form. Okay, so again, this was left canonical. Now we're going to do right canonical. Okay, and the way you build it is again very similar to what we did before. You start with your coefficients, sigma 1, sigma 2, all the way to sigma L.
Yeah, question, in that, if you make the left leg open, then these are just numbers, right? I can just write this sigma L prime and sigma L, then I can get a delta AL, right?
Yeah.
So why don't I get identity?
Okay. Let me go through this in detail then. What you will have to do, what you will get, is a sum for sigma L to sigma small l to sigma big L, for example, or sigma L plus 1, okay? Let's say sigma L for convenience. Okay, of what? Again, you have something like this, right? So you have A sigma L here, dagger, okay? A sigma L. And now you have indices, okay? You have A L minus 1, A L prime. And here you have A L minus 1, A L, okay? And then you have A sigma L plus 1, etc. until dot, 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 A sigma L with then A L minus 1. And this object here is something like this. While this object here is something like this. Correct? Good. And here we'll put a dagger. Okay, A sigma L dagger, A prime L minus 1. So here is something like this. Okay, so now I want to do these contractions, and here actually I do not know so to do the contraction, it's easier, it's better actually. So here I don't know how to do the contraction straight away because these indices are different. So I will start from this side because I have a scalar on one edge. So I will have equal sum, and well, it's just okay, because if you think of it this way, okay, this is once you contract everything, this is something that is shape 1 and AL prime, and this is something that is AL1, correct? This is the shape of this portion here, the shape of this portion here. And you would like to get something that is AL prime AL, right? So I can just do the multiplication from here, and what you realize is that you have something like this, A sigma L, AL minus 1, then multiplies A sigma L dagger, AL minus 1, prime, etc., etc. Okay? But this thing here is basically a U times U dagger in the singular value decomposition. And it's not, generally, it's not identity. In general, this is different from identity. Okay? So,
Not necessarily unitary.
huh?
These are not necessarily unitary.
It's such that U dagger U is equal to identity. Okay? But, okay, now you can see where I'm going maybe, because here we have V dagger. And we know that V dagger V is equal to identity. Okay? So now if I start from the other side and I call this V dagger some B, tack, the problem is solved, and I have the right canonical form. Okay? So yeah, thanks for the question. Hopefully this helps.
What you have done in the past life?
Sorry?
What you have done in the past life?
In which here?
No. There.
Here? What did I do?
In the first line, you should also, you should have the browse, right?
No. I was only looking at the, sorry. Let's put an arrow. This is not equal to this. What I'm trying to describe here is only the bottom portion. I say, okay, the bottom portion, I can write it that way. And then I contract them.
Just the, like the wave function.
Guys, this is just, the wave function below. And then I compress them. Okay? Thanks. Okay, so what I'll be doing here is to reshape it differently from the right. That's why it's called right canonical. So I have sigma 1 until sigma L minus 1, and then I have sigma L. Okay? And then I do an SVD here. And the U will contain all of these terms here. Sigma 1, sigma L minus 1, AL minus 1, and then you have S, AL minus 1, AL minus 1, V dagger, AL minus 1, sigma L. Okay? And what I'm going to do is to call this thing B sigma L AL minus 1, which is a tensor of this form here. Okay, with the physical index here, auxiliary index here. Okay, so this is sigma L, and this is AL minus 1. And the rest, I call it some phi, sigma 1 to sigma L minus 1, AL minus 1. Okay, where I absorb this inside here. And then you continue in the same fashion. I just do one more step, okay, so that it's really, really clear. I reshape this phi as sigma 1 all the way to sigma L minus 2. And then I group sigma L minus 1 and AL minus 1. Okay, and then I have my B, sigma 2 AL minus sigma L, sorry. Okay, and this one I will do an SVD, single value decomposition. And yeah, let's write it here. U, sigma 1 to sigma L minus 2. Then you have AL minus 2. And then you have S, AL minus 2, AL minus 2. And then you have a V dagger, AL minus 2, comma, sigma L minus 1, AL minus 1, B, sigma L, AL minus 1. And again, we call this B, sigma L minus 1, and then you have AL minus 2, AL minus 1. And then this thing, I will call it, I will bring everything else together inside here. Okay, so in this way, you start from a blob like this. And what you're doing is that you start from the left. And this is a B. And then you continue. You do 2. And then, so when both of these are B's, and then you get to something that is obese. Okay, and it's obese, and all the other cases there are all A's because it is because it's normalizing, all right?
So there will be one more free leg, right?
Sorry?
So the series of B which you are taking, there will be one more free leg, I think. The leftmost B will have one more free leg.
Here? No, it becomes a scalar, right? It becomes a scalar. When you fix a certain configuration, you put here a physical index, you get a scalar, right? There is no extra leg here. I'm doing the full wave function. I'm not just doing a portion of the system. I'm doing the full C. from 1 to L. Okay, if I was stopping before, yes, there would be like, but I'm doing the full wave function. Okay, good. Okay, so this is from left or from right, we can contract. Okay, yes.
So the purpose of the canonical form, is it to normalize the wave function?
It is actually to make calculations much faster, and the fact that the wave function is normalized will guarantee that they're all B's or all A's. Now, I want to show to you how this is, for example, used for just an observable. You had a question?
So if we, so the same question, so if we have this psi O psi, for example,
Yes.
the local operator.
I'm getting to this now.
So actually, it depends on the earlier delta function. You will get A1, A2 if A1 and A1 prime are identical, and so on. But then at a place, if you have an operator, you don't have a delta.
Yeah, good. I'm getting to that now. Okay, yes, fantastic. So let me. So we have the left canonical and right canonical forms on this side. So let me look at. You can do an observable, local observable, and then from there many other things will be clear. And to do observable, I will be useful to talk about another representation, which is called mixed canonical.
Sorry, Dario.
Yes.
One question, one observation there actually, not mine, but all of the A's, they are different.
In general, yes.
Yes. So you are calling the same name, they're distinguished by the indices?
By the sigma, yes, correct. And of course, if you have a, in general they're different, and it's a lot, exactly.
They're the same.
Yes, it's regionally invariant, and okay, and you have like a periodic boundary conditions. You can play with different structures where you maybe have the A which is the same, or maybe they have a longer periodicities, or like you have another A and another 2, 3, 4 different A's, and then you continue to this.
But in your
Or you can have.
decomposition, generally they're different.
Yes. Okay. And basically, I point out to them by looking, for example, at the site. So the index L and L minus 1L is what tells me. Okay, so now, let's say I want to compute a local observable. Okay? And how do I do this? And what is convenient is to change our representation, because we know that if this was left canonical, all of them are A's, then I know. Okay, let's do this as a game. Okay, suppose they're all A's. Okay, so I have A dagger here. Yeah. Suppose we do this. Then I know that all of this becomes identity, and I'm left with having to compute something like this. But on this side, I cannot close to identity. Okay? And if there were OBs, okay, let's say there were OBs. I could use this identity properties and bring it to something of this form, but I cannot close on this side. Okay? And let's say this is in the middle of the system, you have to do a lot of calculations, right? So what it would be good is to have something like is a mixed canonical representation where I have some A's and some B's. Okay? And then something in between. Okay, what is it? How do we do that? Okay, the way you do it is the same. And if you think about it, this is actually come quite straightforward from Schmidt decomposition. But anyway, you can start with your initial big tensor. Okay, and you can build in a canonical form. So, for example, you have A sigma 1, A sigma 2. Now, for simplicity, I'm not putting the auxiliary indices below, okay? A sigma L, yes?
So we are doing the ground state problem. Now
We will be getting to the ground state problem, okay? Now I'm trying to show to you how to do look observables, okay? For example, think about the Hamiltonian, or whatever, or let's say you get the ground state. Okay? You want to extract some information from it, right? You want to see correlation, you want to see local property, and so on and so forth, right? So you still need to know how to do these things. Also, the mixed canonical representation that I'm going to describe now is also very helpful when you want to compute ground state properties. Okay, so let me continue. So whenever we were doing this, we realized that at one point we can turn this into a lot of A's and then everything else, right? So this will look like some big phi here, right, with some auxiliary index AL, and then everything else, sigma L plus 1, all the way to sigma L, correct? This is where what I erased just now, no, maybe it's still up there. No, it's not. Okay. So now once you have this object, you can choose, instead of keeping it this way, you can choose to reshape it and do things from the right. Okay? And so I can reshape it and have AL sigma L plus 1 all the way to sigma L minus 1 and then sigma L. And here you can do a SVD. Okay? And once you do this, you get U, okay, all the A, L, sigma L plus 1, sigma L. A, L minus 1, then you have the diagonal matrix, and then you have your V dagger, okay, with all the indices that you need. Okay?
So are we doing these two, that multiples of A, big chunk, and then multiples of these problems?
No, okay, so what I was trying to say here is that if they're all A's, I can use this property that are left canonical and connect this to identity, but here I cannot do this, right? So it would be still quite inefficient to do calculations. If they were all B's, I can do this from this side, but then it would be inefficient. Okay? What you would like to do is to have something that is A from one side, B from the other, and then figure out what is there in the middle. Okay? Sorry? V dagger is B, as usual, right? V dagger becomes B.
So, I mean, if I have a sum of local operators,
Sorry?
so if I have a sum of local operators instead of like in a single size,
Yes.
I have to do it individually for each operator?
You can, and it's actually not difficult. Yeah, because it's all identical. Okay, I will show you.
Okay.
Yeah, remind me in case I don't touch the question, okay? Okay, so now you can see that this thing, you can call it B, okay, for sigma L, and you can build it this way, and you can have something that is A sigma 1, A sigma 2, and then you'll have a B sigma L, B sigma L minus 1, and then you get all the way to A sigma L, okay, and here you'll have B sigma L plus 1, and in between you will have some singular values, AL. Okay? So this graphically we represent it in this way. We'll have A's, and then we have something like this, and then A's again, B's, sorry. Okay, so this object you see does not have any physical index. It's actually the singular values there. So you have S here, then you have all the A's, and all the B's. And this makes a lot of sense if you think about it. The Schmidt decomposition will have for the left, we'll have all the A's, for the B's we'll have all the B's, and between just the singular values. Okay. Now, before I go to this explaining how to compute the local observables now. No, let's do it. So once I have something in this form, now I know how to write it. I can compute a local observable. Because if I have A's here, and maybe the singular value, okay? And then I have a dagger. Then this translates into identity, your A matrix, single value, and then identity. Okay, and here you put the operator. Okay, so it's very, very efficient. What do you, now let's say you want to compute not just one observable, many observable. You can parallelize it very easily, because as long as you know on each side what are these two, what is this object, yeah, then you can compute observables very efficiently.
So how to choose this model, the place where you want the singular value?
How do you choose it? Okay, you can. Okay, this is related to a parenthesis that I wanted to do. Okay, in most of the computations, okay, that we do, let's say for ground state search or time evolution and so on, we do not start from a big tensors like this, and we do this singulars value decompositions, okay, or this big vector. We don't have a very big exponentially large or C, right, with all the coefficients. We don't have that. We don't store that. So this is good to see. In reality, you start from a matrix, which are already from an MPS, which maybe is not in canonical form. You turn in canonical form, and then you work from there. When do we use this to go from many coefficients, a large vector, to a compression this way? Is, for example, in when you want to compress information, and let's say, for example, for some of the problems that we did in machine learning, okay, we had like a vector with a lot of information. We want to compress it. We can try to compress it this way. And there is a lot of more and more work in this direction, using tensor network matrix process states to compress information and do something like that. There were early works already on image recognition. Compression of images. Latorre in 2005, I think. But then many works, and there were some beautiful works in 2016, yes, by Stoudemire and Schwab, where they used tensor networks to do classification problems. Then there was work by Han and Zhang, Wang Lei, and so on. They used this to do generating images. We did some work on sequence-to-sequence learning. Then we did some other works in this direction. So in this case, it's quite useful. But in practice, you hardly ever start from something of this form. What you do is to have MPS in general form, and then you try to go from different mixed canonical representation. Okay, let me give you an example of how you can do this. Okay, say you have yes.
Before going there, can you please explain how we got this? A is
Okay. Because when you go from the left, you reach a point when you do this the last one, and then you're left with the singular values, and the rest will be the left canonical part. Okay, and this is really the Schmidt decomposition where let's say you have psi, we write it as sum over AL, or SAL, and then you have some AL left and AL right. Okay, so AL left is indeed the product. It will be the sum over all the sigmas, of course, of what? A sigma 1, A sigma 2, all the way to A sigma L. L. And A L right is the sum of the sigmas, okay, of B sigma L plus 1 all the way to B sigma. Okay? And now you know that when you do A right, okay, you get 1, right? Because it is in this form. And when you go A left, you also get 1, okay? For a certain index, you get identity here. Okay. So let's say I want to, I have something of this form, since you ask, and it actually would be quite useful for future steps. I have this and this. So this is A, this is S, and this is B. Okay. Okay, I can just look at the SB. Would be S, AL minus 1, AL minus 1, B, AL minus 1, sigma L, AL. Okay? I can do this product, and I call this matrix M. M, AL minus 1, sigma L, AL. Right? I just multiply with this diagonal matrix on the left. And now I do a single value decomposition. And do a U, S, B. But what I do is that I keep the values AL minus 1 and sigma L, and then AL plus 1. Yes, AL, sorry. And then you have S, AL, AL, and then you have a V dagger, AL, sigma L. No, AL. So you see, I have transferred the physical index from something that was B to something on the left, which now I can write it as an A. AL minus 1, sigma L, AL. And now I have this object here, let's call it chi, okay? AL. Actually, it's no, this is prime, okay. AL prime, AL, okay. So I have some object here, let's call it chi. AL prime, AL. Okay? So when I do the single value decomposition here, I'll get another auxiliary index here, which is still at the bond L. Okay? I call it AL prime. And I still have a diagonal one. And then I have the AL back there, right? And then I can bring it together and I have this matrix here. So once you go from this to this, what you can write it as 2 A's later on. But then you have some other matrix here. Okay? And then you have to transfer this matrix to the next step. Okay? You do another single value decomposition. And in this way, you can shift where you have the block here from left to right. And obviously, you can do the other way around, from right to left. And so it's not difficult to shift where you separate between left canonical and right canonical from left to right. Okay? Using, again, grouping the various physical and auxiliary indices as it is convenient, and moving and doing a single value decomposition. Okay. Now, is it really true that you need single value decomposition all the time? Not really. And this is another point I wanted to make. SVD is very useful because once you're having these forms, you can truncate, as we say before, right? When you have you can truncate the lowest eigenvalues, and you're still very close to the wave function. But if you don't want to do any truncations, you just want to turn it to left canonical, right canonical form, what you can do is a QR decomposition. Okay? This, again, if you do QR decomposition, the Q are like the U that we did before. So you can generate left canonical matrix product states by doing left QR decomposition from left to right. Okay, and actually this is convenient because doing a QR decomposition costs, if I'm not wrong, something like OM(n) square, where say M is the large dimension, N is the small dimension of your matrix, while doing an SVD costs about Mn square plus N cube. And so this could be much more expensive, especially when you are dealing with large matrices. Even if N is the smaller dimension, it could still be quite large, okay? So QR decomposition, if you're not doing compressions, this can be very useful. Okay. Okay.
Dario,
Yes?
can you repeat that part, that how you can shift the S? Yeah.
Yes. How do I shift it? What I want to do is to bring in the canonical form, right? I want to shift this block, this B, to be A. Okay? So what I do, I merge these two things. I call it something else. Okay? And then you see here, okay. And now when I'm in the we do the same way as we were doing before. We wanted to generate an A. I will group these two indices together. Okay? And I do a single value decomposition. And now I have something that I can reshape it into my A. And everything else is shifted to the right. Okay? Cool.
How did it become A?
Huh?
How did it become A?
Because it comes from the U. U is such that U dagger U equals to identity, and then it would be so this is the left canonical portion, right? It's also like what we did before. The U's becomes, we reshape it as, we recall it A, and the V daggers as B, right? Cool, fine. Okay, cool. There's something I wanted to say, but I missed it.
Ace V dagger is diagonal, and they call it a chi, something else. But
Oh yeah, but it's diagonal, right?
it's diagonal. But
Yeah.
whether this single values will be preserved, because you are
Sorry.
shifting the whole ace matrix to the right.
Uh-huh.
And
Yes, you push it to the right.
whether the diagonal entries will be the same as this.
Sorry?
Whether the diagonal entries will be the same as this. I mean, this chi is the same as this.
Chi,
Is V dagger.
yes. So SV dagger is chi. Yes. Okay, so now this has no physical indices, so I wrote it something like this.
That is true, but this ace block will not be preserved. And the ace
Ace-
block will not be the same.
A is block. Now I grew. Now from 1A I have 2 A's now.
No, I think he's asking if you move the OC or the OC from one side to another side, will the singular values be the same or will it change?
Now in different bonds you have different singular values. Different bonds. Let me try to also. Yeah, in different bonds you have different singular values, and what is convenient to do is for every site, okay, and every bond, to store both the A version, okay, let's say the generic state here. You store both the A version, the B version, and the single values they have at that bond. Okay, you store all of them. Let's call it SAA. Okay, and then as you update one, you can do the you do the calculations using the ones that you need. Okay. Now so now this is set. We have 24 minutes. Perfect. Let's try to describe how to do ground state search. Okay, which was the objective. Okay. I can erase this. Okay, and here let me go to. Oh, I wrote too much. Okay. Oh, okay. There you go. So this is what we want, and basically I want to minimize, okay, the energy. Okay, I have this. I want to minimize it. So one way I can do it, okay, is to derive, take derivative over, okay, let me write it. Okay, let me write it. So once I have this, I can, let's say I have M here, sigma L, and then I have M dagger, sigma L dagger, okay? If I take the derivative over the M sigma L star, okay? So this portion here, and this is all linear, okay? So I have also ML here, and I have ML, M sigma here. What I'm going to do, what really means is that you are removing this piece, right? Because it's just a product. Okay, so means is that you have something of this form here. Okay. Okay, so what I'm doing, I'm taking the derivative over this piece here. So then I will remove it. Okay, because it's just linear stuff. And then here I have E. Okay, and here I have okay. Now, if I have written my state in mixed canonical forms with all A's here, this doesn't matter, and B's here, okay, this thing very easily, you can see, is E times the piece of MPS there, right? And here, I can rewrite all of this as some complicated object, okay, with three legs here. The local portion of the Hamiltonian, then the other complicated object here, and your local MPS. So the problem becomes to solve something of this type. Okay, and now this may look familiar to some of you because this is a clear eigenvalue problem where all of this thing is some effective Hamiltonian, okay, that acts on something, and then you have equal to that something. So it's really an eigenvalue problem of the type some matrix times a vector, okay, equals to E vector, okay, lambda vector, okay. This represents this big matrix, right? After maybe you reshape your tensor into a vector, and you have the scalar in the vector itself. Yes?
So when you obtain when you had the contraction between A's and B's, how you got the M in that expression?
How do I get the what?
In those M sigma L, M sigma L in the left hand side.
Is that just the name of the...
Yes, this is just the name of the tensor there, right? It could be an A or it could be a B. Or it could be...
is B calculation?
Yes, yes. So to be precise, since we want to use mixed canonical representation, okay, here I will have all the A's, here I will have the B's, and this is, it's the A plus times the singular value, or the B's times the singular value from the other side, okay? It's neither an A or a B, this portion here. Fair enough? Yeah. Right? Okay. It could be an A times the singular value, something like this. Or it could be the B from the other side times the singular value. There is another representation which I have no time to describe to you, but maybe I could, which is known, is what Guiffre Vidal developed, TBD. And then instead of writing A's and B's, it writes all with some, keeping the singular value on every side and some other matrix gamma. So everything is quite symmetric. And you have like a gamma, and then this, lambda. He calls it lambda. Then you have another gamma, then he calls it lambda. And then you have, lambda. And then so on and so forth until the end. But this is equivalent to, so what you will have in the middle here would be two singular values and one gamma as well. Or, because you can bring them together, and something of this shape here would be something of form A, and something this shape here would be B, and then you will be left in the middle with two lambdas and one gamma. Okay?
And why are you differentiating over M?
Because I want to find the minimum energy. I want to solve this problem. Okay? So, pictorially? Yes, hi, sorry.
M sigma L dagger is the H effective.
Huh?
The M sigma L dagger.
It's not in the H effective. I've taken the derivative, right?
No, M sigma L dagger.
Yes.
Upper.
Yes, I've taken the derivative of this conjugate. So it's the one above. See, I've taken the derivative, I removed this one. Okay? So, now, so, sorry? I take the derivative of sigma?
You just remove that part when you're taking.
Yes.
And why?
Because
one gets.
Because it's linear, right? It's like when you do, if I give you scalars, z star a z, right? And then you take the derivative of a z star, okay? You get a z, right? Same. Okay, now 15 minutes, I think we can get the idea how this works, and most of we will continue a little bit tomorrow.
I have a quick question.
Yes?
When you remove it, that basically means you replace it by identity, right?
No, no, it leaves a hole, okay?
Okay, but then
Because, so you see, when you have this matrix times this thing, in the end, it gives you, I have to give you something with three indices, one physical and two auxiliary. Okay? And indeed, you will have one physical index here and two auxiliary indices here coming out.
So you contract it.
You contract everything, see? You get three indices coming out. And so you have the object that you really need. Okay? Okay, so how to do this efficiently though, right? This portion is very easy to do efficiently as long as you always keep left canonical, right canonical form, right? And, but this portion seems that every time you need to do so many calculations because as soon as you put this inside, it's no longer left canonical, right canonical, okay? But you can keep this in memory and move on. And I will try to explain to you how you do this. Okay, so let's say I have this environment. This is called left environment. Left environment. Yes?
So that lower group one that gets detached because you took the derivative with respect to the upper.
Yes, exactly. Yes. So the lower one is what I want to optimize, right? I want to find. So I have left environment L at site, that is a site L minus 1. And then I have the right environment. Environment R at site L plus 1. Okay, some notations in some systems, they use L for the ones that are related to the sigma L, but I prefer to call it this way. Okay, so how is this formed? Okay, let's start from the left all the way, and then let's build it up. You can see that we can compute L1. Then to compute L2, what we need to do is to take L1 and then multiply by the Hamiltonian here. Let's call it W. Okay, so let's put all the. So I do first graphically and then analytically. So I will have L1, and then from here I can build L1 times this will give me L2. Okay, and then L2 times this will give me L3, and so on and so forth. So it's actually efficient to compute all the left environments. Once you start from the left, you build it up. Okay, and the same you can do it from the right for the right environment. You can start from this one, and then you do this one times this, and you build this one. So this is L1, then you right L, okay. This would be right L minus 1, and then you get right L minus 1, you add it to the other one, and you get R L minus 2, and so on and so forth, right? You can build the environments from the left and the right. Fine, but so how I'm going to do all the calculations? The way you do the calculations, okay, let's keep it here, let's go to the side, is in this way. We start from the very first. Okay, start from here, and I want to find a good approximation for this, right? So at the beginning, usually you start with very simple matrix product states, like just product state. So computing all the right environments will be very, very easy. And you keep it in memory. So you will have RL, you build RL, RL minus 1, RL minus 2, all the way to R2. And you have them in memory, okay? And then from this, you can build effective Hamiltonian. You build effective Hamiltonian for site 1, okay?
One thing, can you
Yes?
repeat this notation? I mean, what do you mean by
This?
this arrow?
From here, the next step, I multiply L1 with the MPO and the MPSs at site 2. So here I have, A sigma 2, A sigma 2 dagger, and then the MPO that represents my Hamiltonian at site 2 will be sigma 2 prime, okay? Then you put them together. Now I have L2, and then I have A sigma 3 dagger prime, A sigma 3, and W sigma 3 prime. Okay, and you build up this way. I haven't really explained also some other steps, but okay. Hopefully this is clear enough. Yes?
When you are optimizing the m sigma L,
Yes?
you take derivative with respect to sigma L dagger m sigma.
Yes.
So why can't we take derivative with respect to other m's?
Okay. So you see now what I'm doing? I'm starting from the left here. Okay? And I'm trying to compute the very first one. Okay? But I assume everything here, I know I store it as a B, for example. Right? Fine. Now that I have this, I do the calculation, I find the new value for the better approximation for the MPS at site 1. And it would be, once you do this, you will get a certain M. So when you apply this, okay, it will give you, basically you have a problem of this type M, sigma 1 is equal to E M sigma 1. Okay? And you will get M sigma 1. Once you have this M sigma 1, AL to be precise, then you do an SVD, okay? And we'll write it as A sigma 1, some AL prime, okay? And then some garbage, okay? Let's call it garbage for now. So the next step, what you do, you keep this A here. You still have your operator. And now you want to find the one here. Okay? Now the garbage should have been multiplied by this. Okay? But now we're finding this, so we don't need to care about this stuff anymore. Okay? I have my A here. I have my A dagger. Okay, A sigma 1. Okay, and everything else. Okay? And I will build the new effective Hamiltonian at site 2. Okay? But how to build it? Well, I already had stored all the R's. So I don't need to do more calculations. I will have R3 already stored in my memory. Okay? All I need to compute is left 1. Okay? So I compute L1, which is quite easy. R3. And then if I put together F1 omega here, sigma 2 prime, and right 3, that would be my H effective at site 2. And from this, I can compute M sigma 2. And from M sigma 2, I do an SVD, and I get my A sigma 2, and then garbage. Now I know the first two. These are new, computed. Then I want to find the other. I want to find site 3. Again, I have all in memory the R from before, so I have R4 is already computed in memory. I need to update L2 because L1 I already updated it. I need to multiply L1 by this to get L2. Again, efficient, because I only need to take my L1 is in memory, right? I just need to multiply by these 3 tensor. Okay? And so now from L2 omega 3, omega sigma 3 prime, and L right 4. Okay, I built H effective 3. Again, I will get my M sigma 3, etc., etc. So I go from left to right efficiently. Once I get to the right, then I will go back to the left. Okay? And this going to the right and back to the left is called a sweep. Okay? And in the MSG, you read, how many sweeps you want to do, or what is it? Now you know what a sweep is. Okay? You locally optimize your local tensor, going to the right, and then you're coming back to the left. And every time you see, you don't need to, as long as you, once you compute L at each side, you store it in memory. And then you come back, you need to use the different L's that you did before. Correct? So you don't have to recompute them over and over again. You just need to update them once a new A comes in. And when you're coming back, instead of turning your M into A's, you will turn it into B's. So when you come back, it will be right canonical. And you always be in this mixed canonical representation, which is very efficient. Okay? Question, various questions. Okay.
This one, how is it getting the ground state? When we're solving that H effective, we're taking the lowest
Yeah, correct. And we can do this, and I wanted to describe this, I don't think we will have time, for example, with Lanczos algorithm. You do a Lanczos, and whatever solver you want to use, you don't need to do it, push it to the extremes. Because anyway, you're only updating one local MPS. So maybe you do a few runs, a few iterations of Lanczos, as long as the energy goes down a bit. And then you move on to the next step, you do a few iterations of Lanczos, and then you come back. And in many cases, just a few sweeps can be sufficient. Okay, question there?
So you mentioned that you locally optimize the MPS.
Yes.
For example, in some cases, if it doesn't converge after many sweeps,
Uh-huh.
then is global optimization good for that or local?
Okay, fantastic question. I will maybe touch it a little bit more tomorrow. But this optimization is pretty good, but it can get trapped when you're optimizing only a single site. So what works way better is to optimize 2 sites at a time. And then the conversion is much faster. So now the idea is to find in one go 2. So the tensor that you obtain, M, will have sigma L plus 1, AL minus 1, AL plus 1. Will be an object like this. Now, you can still do whatever we discussed until now. Okay? You just keep the left here and the right here, and so on and so forth. But once you do this, you do an HVD of this object, and you write it as U, AL minus 1, sigma L, AL. Then you have a single value decomposition, AL, single value, sorry. And then V dagger, AL, yes. And then you get all the other things, sigma L plus 1, and AL plus 1. And let's say I'm going from left to right. Let's say I'm doing in this direction. What you're going to do, you just keep this as AL minus 1 AL. And this one, you forget about it. And the next round, what you're going to optimize, you update only this site. You keep this. And now you're going to optimize the other 2 sites. So you optimize over 2, but you shift by 1. And now you're going to optimize these 2. Okay, so you see that this, you actually don't need it. You compute all of this, then you keep this. You update your left environment, and you move on. Okay? Yes?
So why you need to sweep it back? What is the logic to
Well,
from one side and
that forms some biases. So, yeah, it's much more stable. It converges much better if you go forth and back.
okay, it's convolution.
Yeah. Yes. Other questions? Okay, so kind of cover what I wanted to cover. Of course, there are a lot of other holes. Maybe I can try to catch up tomorrow. Tomorrow, I will try to do mostly time evolution and then move on to another method. In case you have questions, I'm still around.
Okay. Are there any other questions?
So what if I, the initial state that I choose,
Yes?
then add the Hamiltonian locally, if the state doesn't have any overlap with the ground state, if I choose such a state, then what actually, why the algorithm fails?
Yeah, So this is the usual method. You start from a superposition and try to. I think you need to have a overlap with the ground state. Otherwise, you will not reach it. Yeah. But it's.
Where the argument fails.
Sorry.
This language where the argument fails.
I think it's your effective Hamiltonian will not cover that subspace.
Okay, so if there are more questions, please take it over the coffee. Now, okay, Shamik has an announcement. Also, let's thank Dario for the beautiful lecture.